So residuals was something we did talk about a little bit. I had mentioned it when we were talking about least squares regression lines. The other word for it was errors. So we're going to make another plot here in a little bit. So given a point xy on a scatter plot, the least squares regression line y hat equals b naught plus b1x. And the residual of the point xy is the difference between y and y hat. So remember that I said if I found a point here, let's not use blue because I already have blue. This point here directly on the line is going to be representing x and y hat. So I put in whatever x is and I get a y hat back. This point here is x and y. So this y is the real value that we had from the data, and this y hat is an estimated value. So the x values are the same value, it's just those y's change. So what we're interested in is this distance here, the distance that we see between those points. That distance is going to be your y minus your y hat. And we're going to call that the residual. Or like I said, sometimes it's called the error. So as another example here, if we look at this point, the real value is going to say that y is actually, sorry, if x is 2,555 square feet, we expect a house is going to sell for 4,000, oh, sorry, not 4,000, $426,000. However, if I plug that into the equation, we get something a little different. That's a typo. That should be 413.6. I'm going, that is way off. If we happen to plug in my 2,555 square feet, then what we see here is that we are going to get my y hat. And what this is saying is that we guess, because like I said, there's other things that could affect a house price of a house. What we think is that if a house is actually 2,555 square feet, then the price is actually 413 sorry, for $413,600. The residual, that's the difference between y and y hat. That residual is actually 12.4. And that is just, like I said, it's just the difference between those two values. So the difference between my estimated value and the actual value of the house was about $12,000. So say basically saying I'm off or have an error of $12,000 in my estimate. That's all it's telling me, which is not a bad, a big amount to be off by. So least squares property. So the magnitude of a residual is just the vertical distance from the point to the least squares line. So all these little vertical lines here are different residuals. The least square line is a line in which the sum of the squared vertical distance is as small as possible. So basically we want one that has this least amount of residual. So it follows that if we square each residual and add up the squares, the sum is less for the least squares regression line than for any other line. This is known as the least squares property. So all that is saying is that my least squares line is going to have the smallest squared sum of my residuals. So the line with the smallest smallest sum of squared residuals or squared errors So line with the smallest sum of squared residuals out of all possible lines is the least squares regression line. Or our line of best fit. So the formula that we had that told us what our least squares regression line made try to find the line with the smallest smallest sum of squared residuals. Really what's using is, like I said, the combination of the averages that you have and the standard deviations that you're seeing in those data in your data. So this is just an example to use. So with the following not with, which of the following lines has wow, I was not doing good that day, has a smaller sum of squared residuals and therefore a better fit for the data. Actually, I remember somebody was talking to me, I was trying to make this. So we're going to look at A. I'm actually going to change this. So I'm going to make a grid here. Okay. So we have X, we have Y. We want to find Y hat, and we want to figure out the difference between Y and Y hat is. So if we look at my data points, I have a data point here at 3, 4, a data point here at 5, 6, a data point here at 5, 9, a data point here at 6, 8, and a data point here at 7, 10. So if I just take those, like I put my 4 in for my X, we'd have the 1.5 times 4 minus 0.5. And that is going to give me 5.5. So the difference between 4 and 5.5 is negative 1.5. So this all here is just going to be the residuals. So if I do this for each data point, oh, not 4, that should have been 3 in there, I'm sorry. I was looking at the wrong thing when I put it in there. It's like, going, that is pretty far off. 3, because X is 3. Actually, if I put that in, I get 4. So I get 4 minus 4, my residual is 0. So that can happen sometimes. And actually, the way I made this line was actually I figured out a linear equation that was between the smallest point and the largest point. So these two should have residuals of 0. But if I do this now and look at X is 5, I get my estimated value, what should have been there, is 7. So my residual is going to be Y minus Y hat minus 1. Well, it's going to be the same for this one because if X was 5, Y hat would still be expected to be 7, but my residual here is going to be a positive 2. Now, if I look at 6, I'm going to get an 8.5. So the difference between 8 and 8.5 is negative 0.5. That's 7. Then I'm going to get 10, and I get a residual of 0. So I want the sum of my squared residuals. So I take each one of those residuals and I'm going to square it and add them all together. So the reason we actually do the squaring, I think I'd mentioned this before, is because we want all these to be positive, because otherwise we're looking at this as distances. We're getting positive distances and negative distances, which we shouldn't have. And it actually kind of like averages itself out, so then we don't actually get any good information. 0 squared is 0, -1 squared is 1, 2 squared is 4, 0.5 squared is going to be positive 0.25, and 0 squared is 0. So we are going to get 5.25 is going to be the square sum of my squared errors. All right, so let's do this with B instead. So if I look at B, this is a different equation, and if I put 3 in, I get y equals 2 times 3 minus 3. So that's going to be 6 minus 3. So I'm actually getting a 3 here. So the difference between y and y hat in this case is positive 1. Now instead of 3, I put in 5. I have 2 times 5 minus 3. That's going to be 7. So my difference between 6 and 7 is -1. Remember, y minus y hat. This will also be 7. So then this difference is going to be 2. Now if we put in 6, we have 2 times 6 is 12, minus 3 is going to give us 9. The difference between 8 and 9 is going to be 1. And then if I put in 7, so that's going to be 14 minus 3, it's going to give me 11. The difference between 10 and 11 is 1. So if I do a square of all of those and sum them up, 1 squared plus -1 squared plus 2 squared plus 1 squared plus 1 squared, well, that's going to be 1 plus 1 plus 4 plus 1 plus 1, which is going to be 4, 5, 6, 7, 8. This one has the smaller sum of squared errors. This is a better fit. May not be the best fit, but is a better fit. And actually, it was this line because, like I said, I made it go between those ones. I think the other one I did was like this. I didn't make a line of best fit for this because I figured it had too many decimals in it. So this may not be the best fit, but this is a better fit. So better fit than B, but not the best fit.